build a retrieval augmented generation prototype on your laptop, everything feels frictionless. You point an LLM at a few dozen PDFs, write a simple script to generate embeddings, and you get instant, accurate answers. But that smooth local environment is an illusion. When you take that exact same code and point it at millions of enterprise documents, while simultaneously handling hundreds of concurrent user queries, the physics of the system break down. This diagram illustrates exactly where that breakdown happens. A stack that works perfectly for a demo shatters against 4 distinct walls when pushed into production. First, your answer accuracy hits a hard quality ceiling. The basic vector search that felt like magic on a small dataset starts returning a pile of near misses when deployed across millions of chunks. Second, your ingestion pipeline buckles. Processing that volume of diverse files, chunking them, and running the compute-heavy embedding models becomes a massive bottleneck. Third, keeping that massive index fresh when source data changes becomes too slow to run continuously. And fourth, as you add complex components to fix these issues, you trigger compounding spikes in both latency and operational costs. A successful proof of concept actively masks these constraints. To build a system that survives real-world deployment, we have to look closely at the math and architecture dictating why each of these walls exists. Pure vector search works by mapping concepts topologically. It understands context and topics beautifully, but because it relies entirely on mathematical similarity, it struggles to recognize exact, specific alphanumeric sequences. Take a look at this retrieval flow. A user asks how to fix error code 0x80000057 on a specific hardware part, PO-001A4-Lima. The system embeds that query and uses cosine similarity to locate the most conceptually relevant chunks in the database. Look at the top 3 results. The first is about errors in general. The second discusses a completely different part, PO-001A4-Paris, which differs by just 1 token. The third is a forum thread with a similar frustrated tone. They are all semantically close to the prompt, but none contain the actual solution. The exact knowledge base article containing the fix does exist in the system, but the similarity algorithm scores it lower than the general discussion threads. The LLM generation step relies on a strictly limited context window, usually just the top 5 or 10 chunks. Because the correct document is pushed out of bounds, the model is forced to generate an answer without the necessary facts. In a small index, this rarely happens, but scale up to 1 million documents, and the database becomes crowded with topically related noise. The true signal drowns in a sea of semantic near misses. Relying strictly on semantic algorithms means your accuracy will inevitably plateau. To retrieve exact technical data, the search architecture requires multiple layers, combining conceptual vectors with exact keyword lexical matching. Getting that data into the database in the first place reveals the next point of failure. Writing a simple, single-threaded Python script to parse and embed files works fine for 50 PDFs. Processing 1 million documents means running trillions of text chunks through a neural network to generate dense numerical vectors. It's a massive compute load. If run sequentially, a single corrupt file at document 950,000 crashes the script, destroying days of work. Instead, an orchestrator-managed pipeline divides the dataset into independent batches, routing them to parallel GPU nodes for simultaneous heavy embedding. Because the architecture is distributed, the system treats each batch independently. If one node encounters a corrupt file and fails, the orchestrator isolates the error and retries that specific batch. The remaining pipeline keeps moving. Scaling requires rebuilding the ingestion layer from a brittle script into a resilient, asynchronous distributed system. That system needs to run constantly. Enterprise data is never static. Policies are rewritten, product specs update, and old manuals are deprecated every single day. If you trigger a full re-indexing job every time a team updates a single document, your compute costs will bankrupt the project. Re-indexing 2 million documents for a few updates is too costly. An incremental pipeline uses cryptographic hashes to instantly detect modified files. It ignores untouched data, routing only changed documents to embedding models, seamlessly overwriting old chunks while leaving the rest of the index undisturbed. Without this kind of targeted efficiency, teams delay syncing their databases simply to save money. The index quietly goes stale. If an employee asks for the latest compliance protocol and the model retrieves last year's version due to update costs, the system has failed. Trust is lost, and the application is abandoned. Every back-end engineering choice eventually surfaces in the user interface. When someone hits enter, they expect an answer in seconds. This graph maps the direct production trade-off. Adding quality components adds latency. Upgrading from pure vector search to a hybrid model running semantic and keyword matching parallel inherently increases processing time. Passing those results through a cross-encoder neural network compounds the delay again. Add in the mathematical reality that searching a massive multi-million chunk index simply takes longer than searching a small one, and your once instant application starts to freeze. To claw back those lost milliseconds, engineers have to deploy aggressive countermeasures. You implement semantic caching to serve up previous answers instantly, and carefully quantize the vector index to reduce memory overhead. You are forced into a constant balancing act. Pursuing perfect accuracy requires heavier computation, which forces you to ruthlessly optimize the infrastructure just to keep the application usable. Beyond the cost of time, we have to account for the literal cost of capital. Look at the monthly recurring costs for a mid-sized production RAG system. At the bottom is foundational infrastructure, embedding fees, search compute nodes, the vector database, and observability tools. But these are dwarfed by the massive LLM inference API fees at the top. Feeding complex retrieved context into an advanced reasoning model requires thousands of input tokens per query. Multiply that by thousands of daily users, and the operational budget evaporates rapidly. Building at scale requires balancing a latency budget and a cost budget against a strict quality standard. When running a demo locally, data is perfectly clean, the search space tiny, and compute is free. But scale up, and the four walls, the quality ceiling, the ingestion firehose, stale data, and cost creep will break the architecture. These walls dictate whether a system survives in production. They are strictly engineering problems, and each one has a specific deterministic fix. In the next segment, we will immediately build out the exact enterprise architecture required to break through them until you try to deploy it to 10,000 users. When that happens, the linear data pipeline shatters. Getting the data into the system and keeping it fresh are standard data engineering tasks. We already know how to build ingestion pipelines, so we will ignore the ingestion phase entirely. To survive scale, the true vulnerabilities lie in just two areas: retrieval quality and the underlying serving infrastructure. A standard query to vector to LLM pipeline collapses under production load. The semantic search returns irrelevant chunks, the context window fills with noise, and the database locks up under the query volume. Handling scale requires abandoning the single vector database. We have to rebuild the retrieval system into a highly decoupled, deterministic architecture, starting from first principles. First, we have to fix how the system searches. Pure dense vector search maps words to concepts in semantic space, but it routinely fails at highly specific, exact strings. If a user queries a hardware error code like 0x80070057, a pure vector index loses it. This diagram shows hybrid search, running semantic vector and lexical keyword searches simultaneously. Unifying them creates a math problem, as their scoring systems differ completely. We solve this using reciprocal rank fusion, strictly using document rank to calculate a new combined score. This assigns distinct duties to each indexed. The dense vector index pulls in chunks based on broad topical intent, while the BM25 keyword index guarantees that exact alphanumeric terms are captured. Running these parallel paths and fusing the results is the only reliable way to force buried, hyper-specific documents to outrank generic, topically similar noise. Hybrid search excels at recall, casting a wide net to find potentially relevant information, but it lacks the precision required to give the language model a clean context window. This schematic outlines a two-stage pipeline. Stage 1 uses a fast by encoder to instantly fetch dozens of rough candidates from the massive corpus. In Stage 2, a heavy cross-encoder scores the query and chunk together, processing joint attention to establish true relevance. Because scoring them together requires significantly more compute, a cross-encoder is too heavy to run on the entire corpus. It must be strictly bottlenecked to the Stage 1 shortlist. We measure the success of this phase using rank-aware metrics. The algorithm forces the single most accurate chunk to the absolute top of the list. even with a perfectly sorted list, we hit a cognitive quirk of language models. They suffer from the lost-in-the-middle phenomenon, frequently ignoring data placed in the center of their context window. To counter this, we place the highest-scoring chunks at the very beginning and end of the prompt, leaving lower-ranked context in the middle. By decoupling retrieval into a fast candidate generation stage, followed by precision re-ranking, you achieve maximum contextual accuracy without breaking your latency budgets. Now we drop below the algorithms, down to the physical hardware layer supporting millions of vectors. As the corpus grows, storing everything in a single index creates a strict bottleneck for search operations. This chart diagrams the infrastructure solution, sharding. We split the vector index across multiple discrete machines, dividing the data into fractions. By executing queries in parallel across these shards, search operations remain sublinear, preventing the database from locking up under severe enterprise load. To solve memory constraints, we apply quantization, compressing vectors from 32-bit floats to 8-bit integers. In front of that sharded database, we install a multilevel cache. If a query hits the cache, the response is free, bypassing the database entirely. This cache operates at 3 levels: storing the final generated response, storing the specific chunk list, or using a semantic cache to catch conceptually identical phrases, even if the exact wording differs. Brutal infrastructure optimization, sharding, quantization, and caching, forms the hidden foundation. It is what prevents your high-quality retrieval algorithms from crashing during traffic spikes. With the data stored and searchable, we reach the deployment layer, serving the actual machine learning models that process the text. This maps out the deployment pattern. We place embedding, re-ranker, and generation models on isolated inference endpoints. An orchestrator batches and routes requests between them. Because each model is isolated, an autoscaler independently adds or removes replica groups based on real-time traffic volume. Notice that the generation model requires significantly more replicas. Text generation is heavily GPU-bound, whereas the embedding models process text much faster. Decoupling inference into independently scaling replica groups ensures that an expensive, slow generation task will never bottleneck a lightweight retrieval query. We have built a massive distributed pipeline. The final architectural requirement is ensuring it consistently produces trustworthy, safe outputs. This flowchart details the trust layer. We implement hard guardrail checks specifically at the final output boundary, right after the language model drafts a response. If an answer fails a groundedness check, the output is actively blocked and never reaches the user. To guarantee stability, we apply strict versioning. We pin the embedding model, chunking logic, and prompts into a single immutable manifest, providing deterministic reproducibility. The primary operational advantage is speed. If you deploy an update and quality degrades, you can instantly roll back to the previous stable state. We established algorithmic quality through hybrid search and cross-encoder re-ranking. We built scale using sharding and multilevel caches, and we secured the system with output guardrails and version manifests. This decoupled structure is the definitive architecture required for a system to survive in production, yet it possesses an ultimate unfixable limitation. It remains a strictly linear pipeline. It retrieves data once and it answers once. What happens when a query is so complex that a single pass isn't enough? When it must autonomously search, evaluate results, and search again? Escaping the single-pass pipeline to create autonomous feedback loops is the exclusive domain of agentic AI, and that is the next phase of engineering.